Everyone, and welcome to the first user success case webinar. Applying geotechnical studies in tunneling with Master of Science Fermin Sanchez. Today, we will talk about a real case study in Mexico in which Professor Fermin Sanchez and his team used PLAXIS to create a 3D geotechnical model to solve a problem that involved a tunnel portal, rock mass displacement, and the construction of a road nearby. My name is Carlos Correa. I'm a product sales engineer for the Geotechnical Analysis Solutions at Bentley. And today I'm honored to have Professor Fermin Sanchez as our guest speaker. Professor Fermin is the director of the Mexico Subterráneo Association. He also is the technical manager at GeoESA company and professor of applied mathematics, numerical modeling, and support system design at the Tunneling Master Program of the National University of Mexico, among other achievements. Thank you so much, Professor, for being here today and sharing with us your expertise. So, what will be our agenda today? I will start with a quick introduction and the housekeeping items of the GoToWebinar platform for those who don't know this platform. And then I will give the floor to Professor Fermin. He will show us a great presentation that he has been prepared for us. After that, after his presentation, I will come back with some information about Bentley and Virtuosity. And to close the webinar, we will have the Q&A session. Professor Fermin, are you ready for the presentation? The audience is all yours now.
Hello, absolutely ready.
Okay.
First of all, I want to say thank you very much to the organization, to Virtuosity Bentley, and also to Juan Carlos Correa for considering me for this presentation, and also want to thank the audience for taking the time to listen to listen and to see my presentation. So this is a case history which I consider very I don't know how to tell, very well. It's very important in terms of all the knowledge that we achieve dealing with this problem. It's basically a landslide, and which is associated with an open cut. And its solution was presented as a cut and cover tunnel in order to stabilize for definitely the movement of a huge rock mass. The movement started at just some meters before the portal of a very big tunnel. Actually, it was not part of the portal. It was a little bit behind, but it was so big, and so some structures, some geological structures, combined themselves in a way that also affected the stability of the tunnel portal. So let's just get into context. This is we're talking about a road. This is the construction of a highway which connects the city of Tepic at the northern western Mexico to the coast of Nuevo Vallarta, which is a very touristic place, and passing through many important touristic resorts and places with beautiful beaches and everything. So in regards to geology, you know, we in Mexico, we have this volcanic system, which is called the transversal neovolcanic axis, which is formed by igneous structures and many types of deposits. Because first we had sedimentary formations, and after that we had all this volcanic activity that created this band, which is colored red in the left image. And in the right image, we can see the tectonics basic structures of this part of Mexico. So the geology and the topography and everything is quite complex, because there are many systems and many types of geological formations, and so this reality makes it very complex to build, or to design and to build geotechnical structures such as tunnels and open cuts and bridges and everything. So it is always a very big channel to a very big challenge to work in this area of the country. And fortunately, we already had many nice and interesting experiences after many years working in this region. So during the construction of the road, it was a very big rock mass started to slide as a consequence of the excavation of an ill-designed open cut. I want to remark this term, ill-designed, and then after the presentation we will conclude that about the importance of well planning, of well risk management and everything. So when the movement started and we started to deal with it, we observed that this failure was caused by the reactivation of an antique geological fault, and this is part of what I called a big design, or a big, or a good design, or a well-planned project, right? And also as I said before, the tunnel portals also started to fail, putting the construction site at a very high risk. And all these combined factors indicated that it would be not possible to stabilize the slide and the portal failure by conventional methods. So, as I said, a considerable rock mass started to slide close to the tunnel portal as this consequence. So now you can see this. So this is an aerial view of the main geological structures. You can see in color blue the main fault, which we call Falla El Jaguar, and there was this other fault which we call Falla Cañada, and the combination of these structures produced this movement. And also you can see here two lines with corresponding vectors of the movement, which formed this kind of a wedge that was moving towards the excavation, the open excavation, and also affecting the construction of the tunnel. And this is another view, and this is what we call the Falla Cañada, the Cañada fault. And here's a place where we could observe this other fault, the main fault, Jaguar. Also, we had also these intrusive materials that were playing an important role in the stability of the problem. Here is an aerial view, the area of the tunnel portal before the tunnel was already excavated. Here we were at the middle of the excavation of the portal, and in this time we started to observe this damage in the front slope of the portal. All these cracks started to appear, as you can see here, and also we started to detect some movements and also these upheavings of some parts of the port of the slope. And now you can see here another big crack, and also we have some local instabilities like this one. This happened while the portal was being excavated. So after all these problems, we needed to design a very much stronger reinforcement of the slope. You can see here these active anchors, and also they were connected with beams and of course shotcrete and everything. And here we can see this zone with a high water flow that was causing also problems. Also here this zone where local collapses were happening, and this other zone of cracking. right? And so then we started with the monitoring and the characterization of the site. This is a representation of the mobilized zone, limited by this principal and secondary faults. And so this was the mass that was moving just right over the tunnel entrance. And this, after we started monitoring, and after many months of monitoring, we got these vectors of movements. The colors are related to the month of the year. This was done during some 1, 2, 3, 4, 5, 6, 7 months of monitoring. And if you take the time later to see the scale, you can see that the horizontal movements of the control points in the area, get up to more than 50 or 60 centimeters of movement of this huge wedge. This is the graphic of the vertical movement of some reference points at the surface, and they belong to the period of June to September of 2017. And you can see also this magnitude of the vertical component was also very considerable. And this is this line corresponds to the time when the tunnel connected with the portal. It was a breakthrough. I will talk about it later, but this is very important information. This is a photograph of the of the tunnel front. In one of the most critical sections, we had this main red fault called the fault Cañada, and also some very altered zones of chloritized rock, and a contact between ignimbrites and breccias, which were also altered. So this situation, I also think one thing that is remarkable is that this tunnel is very big. This tunnel has a cross section to have 4 lanes of traffic inside. So the span of the tunnel is more than 22 meters. I think it's 22 or 23 meters span. So it is a very complicated excavation. So part of the solutions that we proposed was that we should not touch the tunnel portal. We should not perturbate the tunnel portal, or at least to do it in the most soft way. So the connection of the tunnel with the portal was a breakthrough from inside to outside. That was very challenging, and it was an amazing experience. But we did it in a very safe mode, and of course the displacements and everything reactivated in this very moment. But everything fortunately was under control. And so this is a nice view of the tunnel almost finished. You can see the very big span that it has, and this picture is just a nice one. So part of the monitoring also was done inside the tunnel. These vectors are measured. These movements are measured inside the tunnel, and you can see the tendency of these vectors. So the mechanism and the kinematics of this phenomenon was very clear for us. The mode of deformation of the tunnel was clearly indicating that this wedge we defined it was real, and also it was limited in this point where one of the main faults and contact between geological units happened, and also well, this is just after this graphic, we decided that this cross section was the main one in order to study it, the most representative one. And so we took this data from monitoring. You can see at the upper part the control points and the vectors of movement during many months of monitoring, and below this graph, this plot that shows the tendency of the convergence or divergence of the lines between the points, and also you can see the very important magnitude up to 16-17 centimeters of deformation of these lines, which also implied that a problem to finish the tunnel because the form for the final lining was not going to fit, and many things, right? And then with this information, we established the thresholds of action for controlling the behavior of the tunnels, and you can see that the level of actions and the level of alert were really very overpassed. So we had to deal with a very I don't know if dangerous, but a delicate situation. And this is the 2D model that we made of this cross section. It was the objective of this model was to calibrate the behavior of the model with the monitoring results in order to create a realistic geomechanical scenario of the problem and the excavation. This was done before the tunnel was completed. So with this model, we could analyze and then design the rest, the remaining stages of excavation, and as well as the support systems, as well as the final lining structure. And so there are some details of the model, the stages of excavation. A very important issue here is that we utilized for the shotcrete, we utilized the shotcrete model that is available in PLAXIS, which is time dependent. So it's time dependent in terms of the evolution of strength and stiffness of the shotcrete or the concrete. And so this allowed us to represent all the excavation and all the history of this excavation in a time dependent way, and also to get these results in as a function of time. So these are just some plastic points at the end of the excavation. You can see that another solution for this tunnel was to create this curved invert, which was not at the original project. And this is the result of the back analysis, the calibration. So the points are the monitored points, and the continuous lines are the results of the PLAXIS model. So we got a quite a good fit, and this is longer in time. We had up to from September 2017 to June 2018. So it's a long story of behavior. And of course, during the time that there was no excavation, the movements were stable. But then when we made the bottom part of the excavation, also they reactivated. And so this is an important issue. The shotcrete models allow us to work in a time-dependent way. And this is just an example of the results. In this case, the bending moments of the final lining, and this allowed us to make the correct design, structural design. Here is this load capacity diagram with the results of axial forces and bending moments, and it resulted, of course, in the structural design of the reinforcement of the structure. Then we're going to change this. This was the story of the portal, and now we're going to the landslide that was just a few meters behind. This is a view, Google view of the zone before the construction. Well, it was just beginning the construction. You can see here where let me see if I can use my pencil. Yes, this is the position of the tunnel portal, and the tunnel portal would be like this area, and the landslide was all this the landslide, the mobilized mass was this, limited by this first yellow curve, and the real actual fault was behind. So the fault, of course, it moved, but it didn't collapse. But it was the responsible of this of the whole movement. Then these are some views of the zone of the excavation. Now you can see the fault which is appearing here, and also here. So we had a lot of points and a lot of places of good, very nice information to the limit or to represent or to understand and define the real geometry of the fault system and the limits of the movement. Now here you can see some more details. There are also intrusive bodies of volcanic rocks and contacts between different lithologies. This is the position of the main fault, and this is just the contact zone of some intrusive elements. There's another details of the fault, and this is a detail of the main characteristic of the fault. You can see a very clayly material which was wet, and it was with this how do you say well it was the aspect of the main fault, right? Then what we have here, this geological profile took us many months to define it, because there were some places where still the excavations were going on. Of course, we made boreholes, and we installed inclinometers and piezometers and everything. And after many months of work, we had this configuration of the geological profile. The part which is still white is because it was not excavated already, and this position and geometry of the fault was obtained from the boreholes and from the inclinometers, as we will see in the next slides. This is the aspect of the main ignimbrite rock mass, just to see that it was very considerably fractured and quite altered. So this is the main rock mass. And after many months of monitoring the slope, we had these vectors. You can see this monitoring goes from June to April of next year, of June 17 to April 18. So and the magnitude, if you can see the detail, goes beyond 25 30 centimeters in the horizontal component. And also here the colors represent the month of the year. So it was quite a huge movement. It was quite a considerable risk that we had here, and also in terms of time, it was also continuous. But also it was very important to consider that this movement accelerated very much in the rainy season. So we monitored the water table with the piezometers during dry season and during rainy season, and so we had this conclusion that it was very important. The rains were very important, so it was fundamental to consider the groundwater flow within the numerical models. Okay, so let's see. These are the absolute movements and some surface points. So you can see that they are over the 45 centimeters in time in some months, so it is considerable. You can see also the speed of the movements, and these jumps correspond to some excavation activities. These are the results of the inclinometers for many months. So we had a very good results and a very precise position of the fault plane. You can see here we had some strange results. Maybe it was broken something, but we have the very precise location of the fault. And then after many months of characterization and monitoring and everything, we got this solid model of all this zone of the problem. There you can see the main jaguar fault and the other main Cañada fault. And this is the model after beginning the excavations, of course. And in the next slide, you can see the dimensions of the model is quite big, more than 300 meters and more than 200 meters high. And this is a detail of the model when the problem started. It was already excavated, as you can see. The tunnel was not already there, but some of the excavations were already done up to this level. After the movement started, somebody proposed this backfill in order to stabilize. It helped a little bit, but of course it didn't solve the problem in any way. So this is a detail of the a top view of the finite element mesh. You can see the complexity of the mesh is very important. They have lots of contacts, lots of units, very, very complicated geometries, and of course this was a huge work to get this mesh. It took us some months to create it. And this is one cross section that we selected for doing the first calibrations in 2 dimensions, and there you can see the position of the fault. And after reproducing the mechanism, you can see here the water table, and we trial and error process and back analysis. We got this configuration of the deformation of the inclinometers, which resulted. Here's the groundwater flow vectors, and we did it with simulating rain and simulating different positions of the water table and everything according to the results of the piezometers we installed and many things. So we got these results afterwards of the calibration, where you can see the point graphics are corresponds to the inclinometer real results, real data, and the continuous lines are the results of the calibration with the 2-dimensional model with PLAXIS. So up to this point, here's some of the plastic points, and then up to this point, after also we made some cases, we studied some cases of stability. We got a collection of stability factors in different conditions, and we after this point we considered that we already had a good scenario in order to proceed to work with the 3-dimensional model. So this is not a very representative value, this 1.21. This just belongs to some circumstances, but we decided, or we established that we were in a very precarious equilibrium situation, and of course up to this point we still had to excavate all this in order to put the highway, the road here. So it was a very complicated situation. If you can see it more in detail afterwards, these are the parameters we got after the back analysis. I'm not going to talk about them right now. And we started running the 3-dimensional model in order to get the same failure mechanism delimited by the structures we detected, and this is just an example of a potential failure mechanism in 3 dimensions. It corresponds to the actual situation we had in that time, and these are the flow vectors in the 3-dimensional model. Also, we made many cases. We analyzed many cases, and this is, for example, it represents the volume of the mobilized zone, which is 171,000 cubic meters, which is a lot of ground moving towards the excavation. And the best result we got is this representation or reproduction, as you can see it, of the horizontal movement at the control points we had in the surface. So you can see the real vectors are these red ones, which were monitored during the campaign, and the blue vectors are what we got with the 3-dimensional PLAXIS model. So we we said, okay, this is the best result we can get, and up to this point, we can consider that we have created a reasonably approach of the real geomechanical scenario of this problem. And now the next step is to analyze and to design the solution of the stability problem in this point. Okay, so, oh, sorry. So the solution proposed was a cotton covered tunnel. We decided not to excavate anything that was already excavated, but this cut to put here the tunnel, and this that I have that I'm this structure is a pile wall, a very like 1 meter and something diameter piles. Also here are not represented, but with these piles we had these beams here and this very long active anchor system. And so the idea was to excavate little by little, stage by stage, after putting all this pile wall, excavating little by little, and putting the anchor system, and then immediately after to build the tunnel and immediately start to backfill all this region, so we could get the definitive stability solution. This is the structure of the tunnel. As you can see, it's very robust. It's a very strong section with a lot of reinforcement and high strength concrete, and also it's a closed structure in order to work properly with the forces and with a feel inside of concrete. And well, it was a kind of a bunker, they said, but it was necessary. In the 3D model, we put this anchor with cable elements and embedded beam piles in PLAXIS, and we put these beams to represent the union beams of the anchors, and we put these plate elements to represent the shotcrete of this excavation. Here's the picture of the two-dimensional model. So you can imagine, first we put the pile wall, then we excavate in stages, and then we do the rest of the work. Here's a view of the system, of the support system, of the retaining system in the three-dimensional model, and here are some results of stability. So we said, of course, we analyzed many cases with many water flow situations and everything, and we said we are around some factor of safety. This factor of safety is for the, sorry, let me see. No, this factor of safety is for the dry conditions, but we analyze very different levels of saturations and flow, and in the most critical case, we had a factor of safety just a little bit over 1. So it was also decided to have these results because, of course, you have to if you're going to make a model of a very complicated and dangerous situation, you have to depart from a very critical scenario and a very critical stability state, right? So in the two-dimensional model, we analyzed the lining of the structure of the cotton covered tunnel. You can see we have a very fine discretization. We have many elements. This is because we used the time-dependent concrete model available in PLAXIS, and also we simulated not only the excavation but afterwards after we put the tunnel, the filling stages with a very special technique that we don't have the time to describe, but it is a very well studied technique to simulate the correct behavior of a structure like this. These are some views of the model, and these are some results during the backfilling of the cotton cover tunnel. And then here you can see the displacement control. And afterwards, then we had these structural forces. Of course, we got the axial forces in the structures. We got the bending moments, and then we were able to design structurally the cross section and the reinforcement of the problem. And this is the end of the presentation. Unfortunately, this has not been constructed yet. We are expecting to have some participation during the construction, but I think the nice part of this is that we learned a lot of things, and some conclusions that I want to share with you are these that I'm going to read. And they say that many big landslides and big slope failures are caused by mainly because an ill planning of highway projects, and also because of a lack, first, of consciousness and appropriate risk management, and second, because of incomplete and or wrong geotechnical studies. Digging a huge open cut in order to avoid tunneling in many cases results into earth collapse and also financial collapse. We have many cases in Mexico. We have been, during years and years, we have been promoting, also not only us, but also with the ITA and with many institutions, that we should not continue to dig these gigantic open cuts 80 meters tall, because they always end into a collapse, and then it is enormously expensive to stabilize, and there are many financial collapses, economical collapses, terrible ones during construction of roads in Mexico. So we also always say, do not cut the mountains so badly. Make more tunnels, build more tunnels. In the end, of course, at the beginning, everybody thinks that tunneling is much more expensive and cutting is cheap. But in the end, we have demonstrated that in many cases, the solution of the stability problems of rock slopes has been much more expensive than if they, in the beginning, build a tunnel. So this is one of the main conclusions and main messages that I want to give with these presentations. Then another conclusion is that when dealing with a big scale problem like the one presented, the best way to achieve a rational and safe solution, not necessarily cheap, is to recreate the geotechnical scenario of the collapsed system in the most accurate way, in order to be able to proceed with the calculation and design of the reinforcement and retaining structures that will provide a definitive solution, stabilization. And another conclusion is that nowadays the best tools we have at hand and are the powerful numerical codes for geotechnical analysis like PLAXIS. But in order to achieve realistic results, the engineers must have an excellent knowledge of the geomechanical principles that rule the behavior of rock and soil masses, as well as an expertise in the use of numerical codes. This is everything for my part, and thank you very much. And we are getting to the next part of the session. Thank you very much.
Thank you so much, Professor Fermin, for the remarkable presentation. So let me share my screen real quickly. Okay, so just before to go to the Q&A session, I will launch a second poll. So if you have Just a few more seconds. And I think that's all. Okay, so upcoming webinars for those who want to see how other engineers from different parts of the world are using PLAXIS. We are having 2 more case studies. We will have one case study from the US with Jody Robinson, and a second one from Brazil with Luis Olavo from Ensolo Company. So I'm adding the registration links in the chat in case you want to register for these events. And so this week in Bentley, we have a special promotion to celebrate the engineering impact by offering a 20% discount on our annual subscription globally. So if you have an upcoming geotechnical project, you can buy a PLAXIS annual license with a special price this week to avail the 20% discount in the annual subscription. Simply go to our website, virtuosity.bentley.com, and use the promo code engineering20. Okay, so let's go to the Q&A session, Dr. Fermin. So yeah, I think I saw many questions in the chat box. So one question is, how did you model the fold with PLAXIS?
Sorry, Juan Carlos, my computer decided to restart. She takes her own decisions. So I'm back. I don't know if there was a question or something that I have to attend.
Yeah, the question was that how did you model the fold in PLAXIS?
It was a zone, a solid zone with lower properties, of course, of the material. We didn't have the opportunity to make laboratory tests, but we had the samples from the boreholes, and we touched, we analyzed this clay, and so we approximate the properties. And it was a solid zone, and limited by 2 interface elements.
Okay, thank you. Another question is, was the excavation stopped while the monitoring process?
Yes, it was mainly stopped, but in some other places they continued with the activities, but it was mainly stopped. Yes.
Okay. Some guys say that congrats, excellent work. So, okay, so one question, due to the history of the site, will monitoring continue indefinitely after the tunnel portal is complete? How is
Unfortunately not, and
okay.
the reason is one that I mentioned before, that it was of course a financial collapse of the road. So the contractors, they just broke, and the financial system broke, and so they stopped working and they abandoned this highway for at least 5 years. Now they begin again with a new contractor and a new scheme of investment. Hopefully they will succeed this time, but this is not the first time that it happens. It has happened like 3 times. And in many cases of roads in Mexico, this is the story. They start building, everything falls down, and they collapse, and they just resign and abandon the works, and then some years after, then they come again, and then they collapse again, and this is the story, right? And well, it's a very unfortunate story that I can say anything more. Mm-hmm.
Another one, thanks for the webinar, amazing work to solve the slide problem. How do you optimize the parameters, the model with the parameters to match the measured data?
It's a trial and error process. Of course, you have to begin with the realistic properties. Of course, we make all this after the characterization, we make these rock classifications, and we use empirical relationships from Hook and other authors, Barton, Wieniawski, and everything, so we can get the initial parameters, realistic ones. And then we concentrate in the main materials which produce the movements, which are the materials from the fault, and it's a trial and error process, and you have to deal not only with parameters, but you have to deal with time and with the rains, you know, because you have to simulate this in time, so you can reproduce the time where there was no rain, and then the small rains, and then the high rain season, and then the rain goes away again, and all this process, time-dependent process, is what you play with the flow, with the water levels that you monitor it with the piezometers, and you have to basically play with this, right? Rain and parameters, and that's it.
Okay. Okay, so based on your experience, it is possible for the fault or the mechanism to be reactivated again?
According to the calculations, if the cutter cover tunnel and the fill are to be constructed, that should be the definitive solution, hopefully, right? But because as you see in one of the slides, the mass that was mobilized is not the whole mass. The limits of the great fault are beyond this mobilized zone, so hopefully it will not reactivate, but I think the structure is tough and stiff enough to support all the pushing of the landslide, right? So hopefully, yes.
Okay. Well, I think that was like the last question we have. So again, thank you so much, Professor Fermin, for being here, for presenting your work to share with us. So yeah, I know there in the screen there is our email if you want to write to us any questions or anyone to share with us. There is the email. So I think this is the end of the presentation, and thank you so much for all of you to attend the webinar. Thank you so much, guys. Bye.
Thank you very much. Thanks to all the attendees, and hope to see you again soon, and we can keep in touch. Okay?
Thank you. Bye.